But then the last thing I wanted to do here was to talk a bit more about dynamic programming. So dynamic programming is something that we had talked about a little bit last week. And the idea in dynamic programming is it's a way of thinking about optimization problems recursively. Yes. Yes. So yes, dynamic programming, it's a recursive way of thinking about optimization problems where in some optimization problems, you can think of solving the problem for n in terms of solving some smaller problems and taking the best one. So in general, dynamic programming works when you can say, okay, I have several different choices for how to solve the n-sized problem, and I want to go and check several different possible pathways or building blocks to solving n and use the best one of those. Anyway, the naive way of handling this, so recursion is natural, but I'll say naive recursion is, yeah. The problem is if you go and do a naive recursive solution where you go and to solve n, you go and you solve n minus 5 and you solve n minus 13 and you solve n minus 2, that in that recursive call tree where you call this function calls several other functions, each one makes several recursive calls, you end up doing a huge amount of repeated work. You end up solving certain small problems, like solving the size 3 problem over and over and over and over and over again. And this gets to be wasteful and costly. So dynamic programming works for optimization problems that have a natural recursive form, but you want to, let's see. You want to implement this in a way so that you don't end up solving the same problem over and over and over again. So we had an example last time where you wanted to make change. The best way to make change for 6 cents is a penny and a nickel, and you could end up solving this change 6 problem many, many, many times as part of the solution to a bunch of different problems, and that gets slow. So basically the idea, the one thing you want to remember with dynamic programming is to keep track of things you've already solved in an array so that you can check the array and make sure that you don't solve a problem again, because anytime you are about to solve the size 6 problem, go and check your array and see if you've already solved the size 6 problem. And if you've already solved it, don't solve it again. So this was the general approach for dynamic programming. The questions on this general approach, then I wanted to go through one more example today. We had talked at length about the making change problem last time. And this time I had another slightly more complicated problem that I wanted to talk through. Okay. Okay, so let me go and introduce you to another example problem. And I'm going to show you a picture for this, but I want to describe it first, and then I will go and show you a picture. So you have a grid. Oh, this is also incidentally, this is a one of the reasons that I wanted to use this is because I've seen this before as an interview question, in like an interview question for like a software engineering position. So you have a grid. You want to get, you want to walk from 0, 0 to like, say 100, 100. So I want to walk like 100 blocks up and 100 blocks over. And there are many ways to do this. There are many ways. I'll show you a picture in a moment. To do this, I could go north first and then east. I could go east first and then north. I could zigzag. Right, so there's a bunch of possible ways. If I'm going to go, I need to go 100 steps east or 100 blocks east and 100 blocks north. I could go east to north, east to north, east to north, or I could go like a bunch of east and then all the way north and then finish up by going some more east. So there's like lots of ways that you can walk through a grid from point 0, 0 to the point 100, 100. There are a bunch of special points in the grid. How do you walk from 0, 0 to 100, 100? Okay, so this is an optimization problem. There's lots of ways I can walk from 0, 0 to 100, 100. I want to find the one that lets me go and touch as many special points as possible. So if I have this grid here, then what I'm doing is I'm walking from, we'll say, this is like 0, 0, and this is like 4, 4. I didn't want to draw the whole 100 size grid. So I could go and like, this is one option. I could go like over and then up. I could go like up and then over. I could go like this. I could go like this. I could go like that. I could go like this. So I want to go from 0, 0 to 4, 4 using one of these paths. And there's like a bunch of different paths. And, you know, brute force works fine if I'm only going 4, 4. But if I have 100, 100, there's like a lot of different paths. You know, you imagine like paths like, oops, no backtracking. Anyway, so to make this problem interesting, I have a number of special squares. So like, let's say like this is a special square and like this is a special square and this is a special square and this is a special square. So maybe like, yeah. So if I have some special squares, there is no way that I can hit all of these special squares on my path. So yeah, I can't hit all of these, but the question is, how many of these special squares can I go and hit? So like this path here, this hits 2, right? this gives me a score of 2. I go and hit 2 special squares on the way, but that's not the best I can do, because it would be better to go like this and hit 3. So does this problem make sense? Let me go see. Okay. Yeah, so this is the you need yeah, so the limitation here is you only go north and east, because so in order to hit everything, you would need to go and that's, yeah, so let me so you only go north and east. You don't want to go out. You like these red spots. These red spots make you happy, but you're not going to go out of your way for them. You don't want to take more than 8 steps to get from 0, 0 to 4, 4. So you're required to like only go east or only go north. You can't go south. You can't go south and you can't go west, right? So this is like, right. See, any other questions? Yes. So, yes. Yeah, so this could be a graph problem. And there's this could be a graph problem, and there's 100% you could go and solve this using a modified versions of Dijkstra's algorithm. Like 100%. Exactly Dijkstra's algorithm doesn't work, but you could like make this a graph and get something that is like kind of Dijkstra's algorithm. Actually, I think I originally saw this as an interview question. I think one of the reasons this makes a good interview question is because it lends itself well to multiple different ways of solving the problem. You can take a graph approach, you can take a dynamic programming approach, but yeah. Also, the simple greedy algorithm doesn't work very well here. So the greedy algorithm, a natural greedy algorithm would be to say, like, I guess in my mind, the obvious greedy algorithm is to find the closest, you're starting here, find the closest red spot and go to the closest red spot, and then find the next closest red spot and go to that red spot, and then keep going, but like find the closest red spot, the closest red spot, the closest red spot. And that doesn't work, because here, this red spot is farther away, but because it's 2 really close together, then you might want to, it's worth it to go all the way over here and miss this one, even though this one is super close. So yeah. Yeah, so there's multiple ways to solve the problem. Multiple ways to solve the problem. Okay. So, yeah. You can't get all the special squares. And so then also note the there are multiple ways to solve this problem. One uses graphs. Part of what makes this a good interview question. Okay. Also note the obvious greedy algorithm of repeatedly find the closest special square to where you are standing and go to the closest one, repeat until you and the reason this doesn't work is that you might want to go to a further away special spot if it allows you, if it is, for example, in a cluster of several special spots close together. Okay. So anyway, I want to finish today with like, what is the dynamic programming solution to this problem? The dynamic programming solution, so the dynamic programming solution is, so the answer, so to find the answer for 100, 100, or 2, so when we go to our final spot, we are either coming to our final spot, we are either coming from here or from coming to here. So our final solution either goes through 3, 4, or it goes through 4, 3, right? You have to come at this from one of 2 places. And so you either arrive from 99, 100 or from 100, 99. So yeah, so the in general, so let's do it this way. If XY is a special spot, then the answer is the maximum of answer of X minus 1Y. And similarly, oops, okay. If right, so the idea here is, so you want to find the answer for XY. You look at either I come into XY from the west, or I either come in going east or I come in going north. And yeah, So this is like a dynamic programming approach to a problem because I'm solving a bigger problem by looking at the better of two smaller problems. Does this make sense? Any questions about this? Okay. So I'm essentially going and writing down for each square, what is the best way to reach XY? So the best way to reach 100, 100 is going to be the maximum of the best way to reach 99, 100, or the best way to reach 199. I'm going to take the better of these two and then just like keep working backwards. But remember, since this is dynamic programming, you need to have a two-dimensional array that stores the best way to get to xy for each xy. Look in that. Right. So when you solve for, like, say 5, 7, put it in the array, then when you need the solution for, say, 5, 7 to do 6, 7, you look in the array instead of resolving the problem. Right, that's this part here is the dynamic programming idea. This part here is how do you think of this problem as being take the better of two different subproblems. Do we have questions? So we have, so there's two choices for each subproblem, but there's n squared subproblems, right, where this is like two-dimensional. So previously we had looked at like one-dimensional dynamic programming. Here, again, this is like the n equals 4 case. If n is 4, we need to go and we need to store an answer for every square in the array. What is the best way to get to what is the best way to get to here? What is the best way to get to here? What is the best way to get to here? So it's n squared because you have a two-dimensional array. Right, so there would be, yeah, okay, excellent. Yeah, and two choices for, yeah. So this is, anyway, so this is just another dynamic programming example. I like this one because I like, yeah, I don't know, yeah, maybe I like this one just as proof that like this is the kind of thing that some software engineers like to ask during interviews. Okay. Then I think that I am, yeah, so right, this is right. N by N grid, and yeah. Okay. Oh, okay. Yeah, so thank you. So Courtney just wanted me to go into a little more detail. So let me go and like draw some splotches and actually like show you a little bit. So this is like red, this is red, this is red, this is red. So again, we can work from the top down or the bottom up, but the base case is in this corner. Let me go and white this out. So in this corner, the answer, oh no. In this corner, the answer is 0. Right, so the base case is this corner, we can get to this corner, the best we can do for this corner is 0, I'm sorry. The best we can do for this corner is 0 red spots, so I stick this in the array. Then here, to do this one, I look backwards and say, the best way to get here is to start at 0, 0 and go east. And so this answer is 0. Again, along the bottom here, there is only one direction that I could come to get to this square. So it's 0 plus 1 because this is red. This is 1 plus 2 because this is red, or sorry, 1 plus 1 because this is red. So for each of these, there's only one direction you can come. And so we just put like this is 0 because it's 0 plus not red. This is 0 plus it is red, so we add 1. This is red, so we add 1. So the answer here is 2. Similarly, this is like 1, 1, 1. Okay? So then for this square, we now need to look in 2 different directions. It's this subproblem and that subproblem. So the better one of these is 1. Similarly here, here you have either of these are both equally good, so the answer here is like 1. And here, I'm choosing between a 2 or a 1, and 2 is better. Here I'm choosing between a 1 or a 1, so 1 is better. Here I'm choosing between a 1 and a 1, so 1 is better. Here I'm choosing between a 1 and a 1, so 1 is better. Here I'm choosing between a 1 and a 2, so I like the 2. And this then becomes a 3 because it is itself red. 1, 3. That makes sense? Was that helpful? Yeah. So so Eleanor asked the problem of is dynamic programming only really useful for problems that can be? Oh, I'm sorry. My apologies, Ellie. Yes, my apologies. Yeah. So is this only useful for problems that can be represented as a grid? So it is very useful for problems that are either on a line or on a grid or on like a 3-dimensional cube. Let me see if I can come up with an example of ways to. There are problems that are not like obviously represented as a grid where you can still make this work, but it like naturally comes up most often when you're on a grid. The second thing is that, right. And so as Courtney said, you don't have to represent, you don't have to start at the bottom and work up. You could actually start at the top and work backwards. So if you wanted to start at the top and work backwards, you're going to be like starting here and saying, okay, to do this, I need to look at these 2 things. Neither of them are filled in yet. So then I need to go and make a bunch of recursive calls. And I'm going to keep making recursive calls until I get back to the beginning. This is the base case. once this is filled in, then like the recursion propagates. So you can do recursion as long as the important thing when you're doing recursion is to make sure that like for this problem here comes up both this way and that way. You need to make sure once you solve this the first time that you put it in an array so that when you come to this problem the second time, you don't need to recurse. So I will try to come up with an example of a dynamic programming problem that isn't nicely put on a grid. In general, dynamic programming is good for optimization problems. Right, so you don't, so if you work from the bottom up, you don't need recursion. If you work for the top down, then you have recursion, but you check your array before you make the recursive call. Also, getting back to